A skip list is a type of random access list. We can think of a skip list as being created as follows. First, we start with a sorted singly linked list containing, say, n numbers in sorted order. We attach a special node called the sentinel to the front of this list. We call this list, including the sentinel, L0. Now we're going to make a second list called L1. To make L1, we start with the first non-sentinel node in L0 and we toss a coin. If that coin comes up heads, then this node will also appear in L1. If not, then it won't. Next, we move to the next node in L0 and toss the coin again. We will include this node in L1 only if the coin comes up heads. We repeat this for every node in L0. Heads, we keep it. Heads, we keep it. Heads, we keep it. Tails, we leave it. Heads, we keep it. Tails, we leave it. Heads, we keep it. Tails, we leave it. At the end of this process, if any of the nodes made it into L1, then we tack a sentinel node onto the front of this, and this gives us L1. We don't stop there though. We repeat the same process on L1 to get a new list L2. From L2, we make L3, and so on, until eventually we get an empty list. The resulting sequence of nested structures is called a skip list, since the upper lists have edges that skip over nodes in the lower lists. The most important concept in studying a skip list is the notion of a search path. We usually think of a search path as looking for a specific value that may or may not be contained in the bottom list, L0. In this case, we'll consider the search path for 4.5, which is not contained in L0, but if it were, it would be between the values 4 and 5, which both appear in L0. The search path starts at the highest sentinel node and uses a greedy strategy. If the search path can move to the right without overshooting or reaching the value we're looking for, then it does. Otherwise, it moves down. In this case, a right step would take us to 9, which is not less than 4.5. So instead, the search path goes down one level into the list L3. Now, the next step to the right takes us to 1, which is less than 4.5. So the search path goes to the right, to the node in L3 containing the value 1. Now, though, the next step would go right too far again, so the search path goes down into L2. Still, the next step to the right would go too far, so the search path goes down into L1. Now the search path goes right to the node containing 3, again to the right to the node containing 4. Now, though, a step to the right would take us to 5, so we go down into L0. Even in L0, a step to the right would take us to 5. So the search path ends here at the node containing 4 in list L0. This gives us a search path for L4 that takes 8 steps and visits 8 nodes, so we say this search path has length 8. There are a few ways to think about search paths. The way we just described talks about the search path for a value. We can also think of the search path for a node. The path we just described is the search path for the node U in L0 that contains the value 5. The search path for U always ends in the node of L0 that appears just before U. If we think about the nodes at which the search path proceeds downwards, these are exactly the edges of the skip list whose left endpoint comes before U and whose right endpoint is either U or some node that comes after U. Still, another way to think of the search path is in terms of the reverse search path. We can build this path by starting at the node just before U in L0 and repeatedly going up whenever we can. If we're unable to go up, then we go left. Though we don't see it in this small example, search paths tend to be very short compared to the number of elements in L0. This is because they can use very long edges in the upper lists to skip over many nodes in L0. In a subsequent module, we will prove that the expected length of the search path for any node in L0 is only 2 log n plus a constant. The constant 2 is not really critical here, so the thing to keep in mind is that the expected length of the search path is O of log n. We'll finish this lesson by looking at a sequence of larger and larger skip lists. The thing to notice here is that the height of these skip lists, as well as the length of the search path, grows very slowly as the list gets larger.